This presentation has 4 parts. First of all, I will talk about some general aspects. Then I will talk about how to come from present to the future. And then I will present 2 case studies. Let's first start with the general aspects. With waste, disposal of waste, we have the following problem. We all know that radioactive waste is generated worldwide during the application of nuclear techniques, and this includes energy production, science and industry, and also medicine. However, once generated, radioactive waste has to be disposed safely to ensure long-term isolation from the biosphere. I mean, this is pretty obvious. For this purpose, to ensure this, international safety standards have been developed. According to the safety standards, it is required to perform a comprehensive safety assessments of facilities for disposal of radioactive waste. In any of these safety assessments, a key element is the assessment of potential exposures to people after closure of the disposal facility. And these standards also recommend those criteria for the exposure of people. However, here we have a general problem. These safety assessments cover time frames of several thousand years, and in some countries even up to a million years. This depends on the country and the type of waste which has to be disposed of. And disposal facilities have a complex system of different safety features, and therefore, if releases of radionuclides from the waste repository to the biosphere should occur, it will occur only in the very far future. However, compliance with radiological criteria has to be demonstrated today and not in the future. So we have the problem that we have to make assessments of potential exposures of people who live close to the disposal site, but in the very far future. So this problem is that we have to consider very long time frames to enable such assessments. First of all, let me present some information on the radionuclides which are potentially relevant for this disposal of radioactive waste. Usually these are long-lived or very long-lived radionuclides, and most of these radionuclides are not well known because they are so long-lived. First of all, this is for example chlorine 36, nickel 59, iodine 129, and you see all of them have very long half-lives. The longest is uranium 238 with a half-life of 4.5 billion years. Some of these radionuclides have a high potential or are very well transported in the environment under certain circumstances. For example, chlorine 36, selenium 79, technetium 99, iodine 129, and to some extent also neptunium 237. You see, we have very long-lived radionuclides. So what are the time frames we have to consider for safety assessments of disposal facilities? First of all, we have disposal of low-level waste. This is, for example, waste which is generating during the decontamination activities of the nuclear accident. I mean, one example is after the Chernobyl accident or after the accident in the Fukushima nuclear power plant. Usually, the activities concentrations are relatively low, and particularly in the case of Fukushima, most of the radionuclides are not long-lived. Fukushima, the most long-lived was cesium-137, and it requires an isolation time of 700 years. Further on, we have also disposal of intermediate level waste. This is waste which is generated in nuclear facilities, and it contains a broader spectrum of radionuclides, and usually disposal in geological formation is needed at intermediate depths, at around 100 meters or a bit less. The required isolation time is some 1,000 years. The biggest problem is related to the disposal of high-level waste, and this is from spent fuel from nuclear power plants, waste from reprocessing of fuel elements, and here disposal in deep geological formations at depths at around 500 meters is needed. And the required isolation time is 10,000 years or more, and in some countries even an isolation time of up to 1 million years is required. So if you look here at this disposal system, I mean, it consists of different elements. We have the gray part, everything which is underground, and we will not go into details with that. And however, on the long term, we may have also an interaction between the geosphere and the biosphere. And in the long term, radionuclides may be transported from the ground, from the disposal facility to the biosphere. And this is a problem we have to look at in this presentation. And here you see a graph, an image, how radionuclides enter the biosphere. We have the radionuclides in the disposal, migration to the host rock and the overlying rock, and in the far future, radionuclides may appear in the near surface groundwater. There we have two possibilities. First of all, we may have a well, and water from this well is abstracted and used as drinking water, as irrigation water, maybe also as host water for fish production. Or the other case, if we have a very high water table, the groundwater may come more or less to the surface, and this water may be also used as drinking water, or it will contaminate surface soil directly. So this means we have to analyze these two pathways. And this is what you see here. We have the pathways for withdrawal of water from a well. Again, there's the radionuclides in the well water. They come up to the surface water, and we have contamination of fish, but may be also used for drinking water, and very important, for irrigation. Irrigation causes contamination of plant and soil. Plants are used as food, or plants may be fed to animals, and then we eat the animal products as meat, milk, or eggs. However, irrigation also leads to a long-term contamination of soil, which leads to an external exposure to people via dust, resuspension of soil particles, of inhalation, and we have also some processes in the soil which causes a loss of radionuclides from soil as migration and erosion. And we have something similar for the rising groundwater. Most of these pathways are similar. The biggest difference is the rising groundwater contaminates directly the soil, and from soil it goes to plants, and from plants to animals, and more or less we have similar exposure pathways. The key element of that is as the plant models. Here is a plant model for irrigation. We have from irrigation contamination of soil. Part of the irrigation water is intercepted by plant. Activity is lost from plant by weathering, but we have also a contamination in the other direction via root uptake and translocation and resuspension. Within the plant, we have translocation processes, and radionuclides may be transported to the edible part of the plant. And the loss from soil is via migration to deep soils or via wind erosion to remote areas. And here we have similar, but we have a direct contamination of soil from rising groundwater, and we don't have irrigation. So I think this is okay. However, I mean, we have talked about that we have to look for long time frames. The point is, how do we come from present to future conditions? In all these studies done so far, the starting point was always the assessment for present conditions. The question is, what would be the exposure to people if this release from the disposal site would happen today? This is also done to get experience with the site, to learn about the site, and to study all the specific characteristics of the site. Then the next step, we have the environmental change. Environmental change is driven by climate, lifestyle may be different, technology may change, and also the agricultural practice may change. These changes during the safety assessments, these changes are discussed and quantified to allow then an assessment for future conditions. So, first of all, let's talk about the processes causing radionuclide transfer in the environment from the current point of view. Some of these processes were already discussed in the presentation I have given in Tsukuba in February. So let's look for the important processes and features. First of all, we have irrigation. I'm sorry, my throat is dry. We have irrigation. Irrigation demands of the water demand in different crops in different climates. I will discuss this later in more detail. Then we have the processes involved in the behavior of radionuclides in the plants. You see on the right side this image. We have the interception of radionuclides in irrigation water by crops. This is the amount of the fraction of radioactivity which is retained by the plant. Then we have the weathering and loss from plants due to rain and due to loss of leaves, etc. We have the systemic transport of radionuclides in plants and the uptake of radionuclides by crops via the roots from soil and migration in soil. And all these factors have to be quantified. Further on, we have processes involved in the transfer of radionuclides to animals, intake of animals, about the metabolism in the animal, and the subsequent transfer of radionuclides to meat, milk, and eggs. Following the production of animal and plant food products, we still have the processing and the culinary preparation, which may modify activity concentrations in the products. And finally, the intake of food. This is related to the demand for nutrients and how much do people eat. I think I have shown this already before. In more detail, we have the direct deposition on edible plants and the deposition on the leaves. And on the long term, the deposition on soil and the uptake through the root. And pathway 4 is the resuspension of dust and redeposition on leaves and fruit. Let's look for the interception of radionuclides dissolved in irrigation water. The point is, the higher the fraction, the higher is the activity concentration in the crop due to irrigation with water which contains radionuclides. In general, the fraction of radioactivity retained by crops decreases with the amount of irrigation water. The storage capacity of the plants, of the canopies, is limited, and after long rainfalls, only a fraction can be retained. It could be very well observed also after both Fukushima accident and the Chernobyl accident. On the other side, in general, the interception fraction increases with the development of crops. This means the more developed the crop is, the higher is its fraction, because the higher is the interface between rain and plant. And the development of crops is highest during the peak season. So you see here this graph. This graph is where we plotted the interception factor against the rainfall. And at 10 millimeters of rainfall, you see a red line. This indicates a relatively low amount of irrigation water. Usually plants are irrigated at higher rates, at 10 millimeters or 20 millimeters, sometimes even 30 millimeters per application. But you see, for such a irrigation regime, and depending on the leaf area index, the amount of, or the fraction of radioactivity retained is in the order of 10%, 5%, 0.1 or 0.05. So the fraction which is retained is relatively small, even for very well developed plant canopies. The blue curve indicates a leaf area index of 7, which represents a very well developed canopy. So, okay. This is also something that the interception fraction of cations is in general higher than of anions, and this is because of the negative charge of the plant surface. The difference is about a factor of, sulfur and iodine or anions is about factor 2 to 4. Okay, then we have the translocation. Once the radionuclides have been deposited on the plant, it will be taken up by the plant and it will be transported to other organs and tissues of the plant. However, this translocation is not constant for all elements. There we have to distinguish between mobile elements which are transported in the phylum and phloem, and immobile elements which are transported. And here's an error, mistake. It is only in the phylum. So I will correct it right now. Okay, so sorry for this. And transformation depends also on the stage of development, and we have here also a pronounced seasonality. And the translocation for mobile elements is highest during the peak season of the plant development. We have also discussed in previous lectures that the foliar uptake may exceed root uptake by orders of magnitude. And here we see the seasonality or the time dependence of the translocation factor for wheat and barley. And here we see that in particular about 6 weeks before harvest we have the highest translocation to other plant parts. Following the deposition of radionuclides to plants, we have also a loss of radioactivity due to weathering. And this depends on the rainfall, on fog, on foliar abrasion. And usually these parameters also include the degrees of activity due to the increase of biomass. And influencing factors are the time of the deposition, the age of plants, and rainfall or fog. And often this weathering is a quite effective process. The weathering half-life is in the order of 10 to 14 days, depending on the influencing factors. Root uptake of soil is a very important long-term pathway causing exposures to people. It depends on the soil characteristics, on the sorption capacity, sand, lime, clay, the pH value, the redox potential. This means this is a quantification of the amount of air, of oxygen in the plant, and also depends also on the concentration of antagonists, for example, cesium versus potassium, etc. Important is also the chemical performance of the deposit and the time since the contamination. The transfer factor is quantified by the transfer factors for a plant, and this is simple concentration ratio of the activity in plant and the activity in soil. And here you have some typical values for transfer factors for strontium, cesium, but here also for technetium, which is very important, which can be very important in case of when looking at waste disposal. Here you see pretty high values ranging from 0.1 to 10 becquerel per kilogram in plant, per becquerel per kilogram in soil. In general, as you all may know, there's a wide pronounced variability of these transfer factors even on the same site. Another long-term process is the resuspension of soil. And the resuspension describes the flux of radionuclides from soil to the atmosphere, and it depends on the soil texture, vegetation cover, and the wind speed. The higher the wind speed, the more resuspension you have. Therefore, areas which are mostly affected by resuspension are dry, arid regions. In temperate climates, resuspension is not so important, but there are from time to time events during storms which may cause really a relevant loss of activity from soil. And on the long term, we have also erosion on the long term, erosion causes a degradation of soil, and we have also erosion by water. And also see this depends mainly on the slope and on the amount of precipitation, and in particular of the contribution of heavy rain showers to the total precipitation. Because for heavy showers, water erosion is much more important. Erosion also increases with higher fraction of sand and silt. And when we have low contents of clay and organic matter, and for poor vegetation, erosion is higher. And on the long term, erosion might be quite relevant because the annual loss of soil due to erosion may be up to 200 tons per hectare and year. This is equivalent to 1 centimeter of soil. This is a pretty high value. However, if you look at waste disposal, we look at very long time frames. So erosion may be really a relevant loss process. Yes, this is a example. These are some pictures of water erosion. And here you see that this is really an important process which causes a redistribution of material and radionuclides. And we have the next part is related to the transfer to animal products. This depends on the use of contaminated feedstuffs and the transfer of meat and milk. And here on the right side, you see this simple model about activity intake, metabolic model, and the transfer to meat and milk. Usually it is quantified by a transfer factor soil plant, which is defined by the activity, meat, milk, or eggs, and by the ratio of activity in meat, milk, and eggs, and the daily intake of the animal under equilibrium conditions. Usually, if you start feeding, you get this typical curve, as you see in the figure above. You have an increase, and if you stop intake, you have a decrease. Okay, for more information many of these processes and the parameters for the processes are compiled in this handbook of the IAEA, but also in many other publications. So this was more, yeah. And now let me give you a summary of the first part. We have seen that licensing of facilities for disposal of radioactive waste require a safety assessment. And the safety assessment is a key element of, the assessment of exposures is a key element of the overall safety assessment of a disposal facility. We have long time frames to be considered. It's ranging from several hundred years for low-level waste to 10,000 years and more for high-level waste. Important pathways for radionuclides to enter the biospheres are the abstraction of water from a well, and secondly, also rising groundwater if we have high water tables. In this safety assessment and in these assessments, we have to include all relevant pathways, including the intake of food and drinking water, inhalation of resuscitated soil, and external exposure. And also in the safety assessment, we have to consider all processes leading to an exposure of people, including irrigation, uptake of radionuclides from soil, radionuclide sorption and migration in soil, as well as the transfer to animal products and the erosion and resuspension. This was a summary of the first part, and I propose that we start with the next one, let's say in 3 minutes.